Welcome back, everybody. This lecture is all about compact sets. Now, the next few minutes are going to be really, really cool because I'm about to show you what I think of is really just about the most incomprehensible set of definitions in all of undergraduate mathematics. This is awful to try to understand the first time you see it. I can clearly remember sitting in class the first time I saw the definitions that are about to pop up on the next slide here, and I remember thinking, this teacher is smoking something really good. I mean, whatever he's got a hold of, he needs to share with the rest of the class because this is just not right. So let me show you what I'm talking about. The really cool thing about this is within the next few minutes you will not only understand what this definition means, but you'll be able to use it, and that's a really cool thing because I'm going to explain it to you in a way that even though it's incomprehensible now and will be for a few minutes, in a few minutes it will be very comprehensible. So here's how it goes. Suppose that we have a set of real numbers. We'll call it S, and we'll use blue to denote that throughout the next few minutes of our time together. And we have a collection of open sets. So that's like a set of open sets. Okay? And we called that set scripty F. So if you notice that weird looking symbol there, it's not a dwarven rune, even though maybe it could be. That's a German Fraktur font, scripty F. So I'll usually call that scripty F. But we usually use the old German Fraktur fonts for collections of open sets like this. So that's a scripty kind of F. Okay, so scripty F is a set of sets. Okay, so it contains a whole bunch of sets, and when you union all those sets together, it contains the original blue set S that we were talking about. We call then scripty F an open cover of S, and we say that S gets covered up by scripty F. And then suppose we had a scripty G. Again, that's a G. Again, looks like some sort of freaky medieval rune, but again, that's that old German Fraktur font. Scripty G is a collection of finitely many sets that come out of scripty F. It's a finite subset of scripty F. If scripty G covers S, then we call it a finite subcover of the original blue set S. Okay, I promised you this was incomprehensible, and it really kind of is, right? The first time I saw this, I remember being absolutely dumbstruck at what in the world is this teacher talking about. This was, I thought, completely bewildering. But it's really not that bad. So we're going to go through this slowly and carefully, and in a few minutes you'll be able to show this to your friends and completely understand everything that it says. So here we go. I'm going to draw you some pictures because that's the key to understanding this. So first off, what's an open cover? That was the first thing we defined. Well, we have a blue set S. So you'll see that the set there in light blue, that's my set S. Okay? And an open cover of S is a whole bunch of other open sets, okay, that we throw together to make a big collection of open sets. And so I'm going to drop in some other open sets. Okay, notice they're rounded on the sides. It's supposed to kind of like parentheses to make it look like those are open. Okay, and you notice I'm dropping them all in there. Okay, and as I add more and more and more of them, you can see that now they have covered the blue set in the sense that you don't see the blue set anymore. What you see are all the sets that are laying on top of it. There's a charcoal gray one and another kind of blue and white and purple and all sorts of other colors. You don't see the blue underneath it anymore. Okay, so another way of saying that it's covered up the blue set is that if I took the union of the purple and the green and the yellow and the white and all of those other colored open sets there. If I unioned all those up, what I would get is, well, in this picture, an interval from the leftmost charcoal gray set to the rightmost purple set. Right? It would be another open set because I'm unioning open sets. And the original blue set S would be contained in that union because again, it's underneath all of those other sets. Right? But again, thinking of it this way with a bunch of sets literally covering and laying on top of S makes this make a lot more sense. So, a collection of these multicolored sets here, right? A whole bunch of sets. blues and whites and purples and yellows and greens. Um, a collection of sets like that, right, that covers up my blue set S is an open cover of S. Make sense? If that didn't make sense, rewind it about 45 seconds. Try it again. Don't go on until you understand this idea that an open cover is a collection, a whole pile of open sets. And when I put them all down together and union them up, right, or imagine that they're laying on top of my blue set S, right, then they completely cover my blue set. Okay? All right, that's an open cover. Okay, what's this subcover business that we talked about, right? So what we just saw was like a scripty F, right? A whole bunch of open sets that covered S. A subcover, and in the definition a second ago, I was using scripty G for that. Well, a subcover is like a subset. It's just part of the original cover. So here's what I'm going to do. I'm going to take some of those sets that you see there, and I'm going to just rip them out. So I'm going to drop away that one. Now let's get rid of one more. Okay. So I've pulled out three in this case of those original open sets that were part of the cover that we saw a second ago. Okay? What's left is still a cover of my original light blue set S, because you'll notice I don't see any light blue. All those multicolored sets, gold and yellow and purple and white, those are all still covering up the original light blue one. So again, if you took the union of all those multicolored sets, they would contain the original set S, which is buried in there underneath it. So again, literally, the blue set is being covered by those remaining sets. And it's a subcover of the original one because it has fewer sets in it. I've taken some of those sets out. It's just like a subset is a set, that is related to the original set by getting rid of some elements. Here I've gotten rid of some of the open sets that are supposed to be doing the covering, and what I'm left with still covers my original blue set S. Make sense? Okay. All right, so let's go back to the definition again, and I think that will make much more sense this time. So suppose you have a light blue set S, and scripty F is a collection of open sets that cover S. Okay, well, it will be an open cover of F if S is contained in the union, just like we saw in the picture a few minutes ago. Again, you really should imagine S as being an open set, and scripty F is a whole bunch of other sets that you throw down and they literally cover up S so that you can't see it anymore. Okay? Now, if I throw away, right, a bunch of the sets in F, and what's left is only finitely many sets, right? And it still covers S. We call that scripty G. Then scripty G would be a finite subcover of S. Okay, now you notice in that picture a few minutes ago, all the things I was doing were finitely many of them because I don't have time to draw infinitely many multicolored sets on the screen. Right? But we'll see in these examples in a second where the fact that we can cover up S with only finitely many open sets, well, sometimes it's not true. And when it is, it's really important. So again, this is a really bewildering definition when you first see it. But in the last, 10 minutes or so, we've gone through this carefully, and I hope this has all made sense. If it hasn't, zip the slider back a little bit, rewatch it again, because this is really, really important. You won't be able to understand what we're going to do with these open covers and stuff if this part doesn't make sense. But the really cool thing is, I think, after you've gone through and watched the animation, I believe that this will make lots of sense. And now this completely confusing and bewildering mess of scripty F's and scripty G's and weird symbols, right? That's something we understand now. Okay, so why do we do all of that? Well, it's for this next definition. So here's what we really want to define. We want to define what it means for a set to be compact. So a set S, which is in the real numbers, and say we still color it light blue, that set will be compact if every open cover of S has a finite subcover. Okay? So again, this is the sort of thing that you'll have to memorize because I might ask you to state what the definition of a compact set is, and you'd say every open cover has a finite subcover for my set S. Okay, so you're used to saying that. What in the world does that mean again? Right? Well, first off, notice this is a quantifier statement. This is why we did all that logic stuff ages ago. Every open cover, not just one open cover, but every open cover has to have a finite subcover. That means if I take an open cover script F, right, then I have to be able to throw away all but finitely many of the sets I'm using. And what's left, call that script G, with finitely many multicolored sets left, that still has to cover my original set S. Right? So it means it won't, no matter how many sets it took to cover S the first time, I can always get rid of all but finitely many of them. That's a really cool thing because it means that we can sort of go from working with a whole bunch, maybe infinitely many open sets, to working with only finitely many of them. That's really, really powerful. Compact sets are super important, and we will see why as we go through the next several lectures. Okay, this desperately needs an example. So here's an example. Let's let S be the closed interval from 3 to 5. So includes 3, includes the 5. And let me give you an example of what an open cover might look like. So here's what I'm going to do. I'm going to look at every point X, which is in my set, and I'm going to make an open set that contains that point X. What I'm going to do is I'm going to let UX, I'll use U for open sets for the next little bit. I'll let U sub X be the open set, which is just the neighborhood around X of radius a half. Okay, so okay, this needs an example. What does U3 mean? Right. Well, what I mean by U3 is it's the neighborhood around 3 um, with radius a half. In other words, I go a half on either side of the 3. So U3 would be the interval from 2.5 up to 3.5. Okay. What would be U4? Well, U4 would be the interval from 3.5 to 4.5, and so on. You don't have to have, of course, whole numbers, obviously. You could have U sub pi, that's also in this collection. That would be an interval centered at pi, and you go a half on either side, right? Because remember, pi is 3.14-ish. Okay? So every number between 3 and 5 gets an open set, right? That's 1/2 a unit in radius, sitting around it. Okay? So for every point in S, all uncountably many points in S, all those uncountably many numbers between 3 and 5, we get an open set. Now, obviously, if I union all of those open sets together, then that will completely cover up my interval from 3 to 5, right? Because every X is inside UX, right? So if I union all the UX's together, then of course um, I'll get more than the interval from 3 to 5, right? Because of course, like I said, notice that U3 lops over a little bit, past 3 down to like 2.5. So all these intervals will definitely cover up the interval from 3 to 5, okay? All these U's. Okay, but what does it have to do with the subcovers and how does all that work? Well, think about this. We really don't need all of those sets, right? We had one set for every point in there, and you don't need that many to cover up 3, 5. Here's an example. There's lots of ways to do this, but let's just think about this way. Suppose I took U3. Okay, U3 will cover everything from 2.5 up to 3.5. Okay, then let's throw in, say, U3.8. So U3.8 would be an interval, if I go half in either direction, they'll go down to 3.3 and up to 4.3. So now, if you imagine the interval 3, 5 as my blue interval, right, and I start laying down U3 on top of it, I've covered over all the blue part up to 3.5. Now I lay U3.8 down on top of it. That overlaps the first one and covers up even more blue from 3.3 up to 4.3. Now let's try, say, U4.7. So that'll go from 4.2, right, up to 5.2. Right? And now you see with those three sets, I've completely covered up all the blue of the interval from 3 to 5. So just those three sets would be a subcover, and it would be a finite subcover of my original. Because again, I don't need all the possible intervals that I could make. I just need like those three would be enough to have them overlap enough to cover over the blue interval from 3 to 5. Right? Now, this doesn't prove that the interval from 3 to 5 is compact. Because remember, what does it mean to be compact? this is a quantifier problem again. We have to show that every open cover has a finite subcover. So to prove for all, I don't do a particular example. Remember that from all our stuff with logic. To prove a for all kind of statement, I have to do this with like a variable, a generic something, and show that it always works. Um, it turns out that the interval from 3 to 5, if I include the 3 and the 5, that is compact, and we'll see why in a few minutes. But I want to mention that um, I did this example so that you see what an open cover and a finite subcover are actually supposed to look like, and give you some kind of handle on how that works. But this isn't a proof yet that the interval from 3 to 5 is compact, even though it is, and we'll see why in a few minutes. Okay, another example. Um, Unbounded sets can't be compact. Doesn't matter. If it's unbounded, there's no way it can be compact. Again, I'm not going to do a proof of this exactly, but I think if I give you one quick example, you'll see how it always has to work. So let's look at say, an interval from 2 out to infinity. Okay, so that's unbounded, right? Starts at 2, has a lower bound at 2, but no upper bound. So this interval runs from 2 to infinity. And here's how I'm going to cover it, right? Now remember, to show that this is not compact, right? Well, I'm proving the negation of a, for every open cover, there's a finite subcover, right? And remember how this works. If you prove the negation of a for all, that means you have to prove there exists. So the negation of the definition of compactness would be there exists a finite subcover, which, sorry, I said that completely backwards. So what do I need to do to prove this is not compact? I need to show that there exists an open cover which doesn't have a finite subcover. And that I can do because I just have to make one, and it's pretty easy. Here's my open cover that does not have a finite subcover. What I'm going to do is I'm going to look at intervals, kind of like I did a few minutes ago. I'm going to use open sets UN, where each UN is the neighborhood around n of radius 1. So like U3 would be the interval from 2 to 4. U7 would be the interval from 6 to 8. So I go 1 unit on either side. Okay. Now, of course, that obviously is going to cover up all of my interval from 2 to infinity, because what's u1, right? Well, u1 runs from 0 to 2, right? u2 runs from 1 to 3, and so forth, right? Um, okay, so I union all of those up, and clearly that will cover up all of the numbers that are bigger than 2. But it's also kind of obvious, if you think about it, that no finite collection, no finite sub collection, right? No subcover of these could actually cover. No subset could actually be a cover, right? Because if I only had finitely many of them, right? Suppose there were only 100 of them, right? Well, it doesn't matter how large the n is, right? There would have to be a maximum of them, right? If there's only finitely many of them, it can only go so far. It couldn't reach all the way out to infinity. That makes sense? So in other words, suppose that these were covered by a whole bunch of sets, and the biggest set was U100. Well, everything after, all the numbers after 101 don't get covered. And if there's finitely many, there'll be some largest set, right? So in order to cover this unbounded set, I'd have to have infinitely many of these small open sets to completely cover it all the way out to infinity. That's why unbounded sets can't ever be compact. And so if you had any unbounded set, you could play this same game. It's obviously, I think, how you would go through and rig up the proof. But again, I think that, well, you can read the proof in the textbook, but showing you an example with real numbers, because this stuff can be a little confusing, is probably more helpful here. So, okay, so unbounded sets can't be compact. It also turns out that open intervals can't be compact. Oh, okay, so we're throwing out a lot of stuff, right? Um, Unbounded sets can't be compact. Open intervals can't be compact. How does that work? Well, okay, so let me show you another example. Let's look at the blue interval here from 0 to 2. Okay, now here's how I'm going to cover it up. Now remember, I'm proving that this interval from 0 to 2 is not compact. Okay, so all I have to do is show you one counterexample, right? All I have to do is show you one open cover that does not have a finite subcover. So here's my example. Here's my open cover. These are all the sets that go from 1 over n up to 2. Okay. Okay. So that desperately needs a picture. So here we go. So here's the real line. I've hopefully labeled 0, 1, and 2, and I'm going to draw in my blue interval from 0 to 2. Again, open set from 0 to 2. Now I've colored in these UNs green there, and I'm going to sort of show you what the first few look like in increasing darkness of green. So what would U1 be? Would be the interval from 1 over 1 to 2. Of course, 1 over 1 is just 1. So U1 would be that first interval. It would run from 2 back to 1. Again, usually we're used to think about these things from left to right, but I deliberately did it this way so that you'd see how 1 works if we kind of go in the other direction. So U1 would go from 1 over 1 to 2. Okay, what about U2? U2 would go from 1 over 2, that'd be a half, to 2. So this now stretches a little further. Starts at 2, but goes all the way back to a half. What about U3? U3 would go from a third to 2. Right? See how that works? Then what about U4? It stretches a little further from 2 back to a fourth, or reading it the way we normally would, it'd be the interval from a fourth to 2. Okay? And of course, you see what's happening here, right? Um, if I keep doing this process, I'm eventually going to cover up all the blue, right? I'll keep adding more and more sets, and I'll eventually cover up all the blue. But it'll take all infinitely many of them to do it, because you give me a blue spot, eventually it will get covered over, right? So the union of all these infinitely many sets will cover the blue. But what happens if I stop at some point, right? If I only took finitely many of them? Well, if I ever took finitely many of them, then that would still leave me some blue uncovered. Okay? So it would take infinitely many of them before we finally get every blue point covered. So no finite subcollection of these sets can cover all of 0 to 2. Therefore, I've created an open cover that doesn't have a finite subcover. All right, so we know that these compact sets, they can't be bounded, doesn't like they can be open. So what are these things? Well, I'm glad you asked. I have an answer. So the answer is the famous Heine-Borel theorem. So this is the kind of thing that people who've had this class, where you studied beginning analysis, this is one of the things that everybody remembers. So the Heine-Borel theorem says that a set of real numbers is compact if and only if it's closed and bounded. That's the deal. So why the weird definition, right? Why all that open cover and subcover thing? Why didn't we just say compact sets are closed and bounded? Well, the open cover and finite subcover business is really cool, because knowing that will let us do some cool things with these compact sets. And we'll see lots of examples of that as we go through the rest of the class. But it turns out that for real numbers, these compact sets have to be closed and bounded, and that's all they have to be. So any set that's both closed and bounded is compact. Now, I feel obligated as a mathematician to pause for just a tiny second and tell you that this works if we're talking about sets of real numbers. If we're talking about sets of things that aren't real numbers, then there is a version of the Heine-Borel theorem, but the right word is not closed and bounded. It's complete and totally bounded. There, I've said it. So you can pretend like I didn't say that, but my contract as a mathematician says that I can't just let that go, because there are things that aren't there are sets that aren't just full of real numbers. For our purposes, we won't worry about any of that, and I won't say that ever again the rest of this class. But if you take further classes in analysis, then you'll run across that there's a more complete version of the Heine-Borel theorem. But as long as we're talking about real numbers, and for us we always will be, it means that a set's compact if and only if it's closed and bounded. Okay? So the other famous theorem that we have to state at this point is the Bolzano-Weierstrass theorem. It says that every infinite bounded subset of R has to have an accumulation point. So we will see as we develop the language of sequences in the next few lectures, that there's other cool ways of saying this using the language of sequences. But this is good enough now to go ahead and say it so that we'll be able to use it later. So if we have an so what does that mean? Infinite bounded subset. What I mean is it's a bounded subset. Okay. What does the infinite part mean? I mean it has infinitely many points in it. So if you have a set that just has like the points 1, 2, 3, 4, 5, that's all. Okay. That's bounded, but there's only 5 numbers in it. So what I mean is this set has to have infinitely many numbers in it. Okay. If you have a set with infinitely many numbers in it, but it's still bounded, like that interval we saw a few minutes ago, the closed interval from 3 to 5, that was an infinite set in the sense that it has infinitely many numbers in it, but it's still bounded, right? Bounded below by 3 and above by 5. So if you have a set with infinitely many numbers in it, but it's still bounded above and below, then a set like that has to have an accumulation point. And remember, what's an accumulation point, right? Well, a point's an accumulation point if, remember from previous lectures, if every deleted neighborhood around it intersects both the set, well, intersects the set. That's the way to say it. Okay, so how are we going to do this? I'm going to do this by contradiction. Okay? So again, we did all that stuff with logic and all of the stuff working through different kinds of proofs. Exactly so, we would be able to get to a point like this and know what it means to do a proof by contradiction. So here's how it works. What we're going to do is suppose that we have a set S, which is infinite and bounded, but it doesn't have any accumulation points. Okay? So again, if you think of the Bolzano-Weierstrass theorem, you could rewrite that as a P implies Q. That if S is infinite and bounded, that implies that it has an accumulation point. So how do I do a proof by contradiction? I assume P and not Q and show that that gives me a contradiction. So I'm going to assume that S is a subset of the real numbers. It's infinite and it's bounded. That's the P. But not Q, that it has no accumulation points. Okay? It gives me a lot to work with, notice. This is why I like doing proofs by contradiction, because I know a lot about this set S. I know it's infinite, I know it's bounded, I know it has no accumulation points. There's a lot to work with there, right? I can start writing down stuff and trying to get a contradiction, and I got somewhere to go. Well, first thing, since it has no accumulation points, it has to be closed. Okay, wait, why is that? Well, remember, one way of saying that a set was closed is to say that it contains all of its accumulation points. And if there aren't any accumulation points, then the set of accumulation points, S prime, is just the empty set. And of course, the empty set is a subset of S. Okay, so if it has no accumulation points, then it has to be closed. Another way of saying that is it has to equal its own closure, which of course is always a closed set, because the closure of S is S union its accumulation points. And if there are no accumulation points, then S union the set of accumulation points is the same as S union the empty set, which of course is just S. So S has to be closed. That's cool. We already assumed it was bounded. So by the Heine-Borel theorem, we know that S has to be compact. Right? So what we've assumed so far is that S was infinite in the sense that it has infinitely many points, that it's bounded and no accumulation points. The no accumulation points tells me it's closed. The bounded, together with that, tells me that S has to be compact. So here's what we're going to do. I'm going to start playing with open covers and such. Let's pick a point X that's in our set S. Okay? Now, X is not an accumulation point, because remember, we're assuming there aren't any accumulation points ever. So whatever this point X is, it's not an accumulation point because there's not any. So what does that mean? Well, that means that if I took a deleted neighborhood around X, that it won't intersect S for at least some value of epsilon. Right? Because remember, what does it mean to be an accumulation point? It means that for every epsilon, the deleted neighborhood around X of radius epsilon does contain a point in S. So the negation of that would be, I've changed it for every epsilon to a there exists when I take the negation. The negation will be there exists an epsilon, and I'll write epsilon sub x so I know which epsilon I'm talking about. It's the one that goes with this x. There is an epsilon sub x so that the deleted neighborhood around x with radius epsilon sub x that doesn't contain any points of S, which means I could intersect it and get the empty set. That's another way of writing that. So cool. Okay. Um, well, what was this deleted neighborhood thing again? If you remember, the deleted neighborhood, the n star, means the neighborhood without the star, and then I throw away the x. So n star x of epsilon sub x is just the neighborhood x comma epsilon sub x minus the x itself, right? That's why we won't. That's when we're talking about an accumulation point. We always have to throw away the x because, of course, obviously x is in S, but nothing else around it is, okay? Because it's not an accumulation point. Nothing in S is accumulating, piling up, getting really close to x, right? So if I look at the whole neighborhood in x epsilon sub x, that's an open set, obviously, because it's an open neighborhood. Right? It contains x, right? Because x is at the center. Right? But the deleted neighborhood didn't contain any other points in S. That means that x is the only one in there, because obviously the whole neighborhood, contains x, but the deleted neighborhood didn't contain anything else that was in S. So this means that I've gotten an open set that contains x but nothing else in S. And then I just repeat that for all the different points that are in S. And at every point in S, I get a little open set that contains x but no other points of S. Right? That means if I union all of those together, of course it will cover S, right? The union will contain all of S because every point in S is contained inside one of these neighborhoods. Right? But this is a problem because S was an infinite set. That means that I have created an infinite open cover, right? But S is compact, which means that every open cover, including this one, has got to have a finite subcover. And why is that a problem? Well, because if I looked at only finitely many of these sets, right, then I'd miss stuff. Because remember, each of these open sets contains one single point of S. So I need all of them. As soon as I throw one away, one of these neighborhoods, I'm not covering up one of the points of S anymore. Each neighborhood covers up only one point of S. So I can't get rid of any of them and still have an open cover, much less get rid of so many that I only have finitely many left, right? So there's my contradiction. I have an infinite open cover, right? This does not have a finite subcover. So that contradicts the assumption that S was compact. So there's my contradiction. Okay, so why am I so excited about compact sets, right? I mean, when I first heard this compact sets, this sounds like a really small car, right? So we show up at the car rental agency and says, yes, yes, I'd like a compact set, please. Give me the economy size or whatever. I can't afford the SUV. So what's so special about these compact sets? Well, here's the heart of what it is. Compact sets often act like finite sets. Now, remember, they don't have to be finite sets. I mean, like I said, they could be uncountable. But sometimes they do stuff like a finite set would. And finite sets are really cool because if I've got a set with like 13 things in it, then that's great. I can list them all out. I can do what I want to. With 13 things, it's not very many. And compact sets, even if there are again uncountably many points inside them, a lot of times working with them is a lot like working with just finitely many things, because you could cover that compact set with just finitely many open sets and then just use those finitely many open sets for things. And we'll see lots and lots of examples of that as we go through the rest of the class. Here's just one example. Compact sets always have to have a max and a min. If you think back to our lecture when we talked about sups and imps and so forth, compact sets will always be bounded, of course. So they'll have a sup and an imp. But because they're closed, right, they have to include those accumulation points, those soups and imps. So those soups and imps will actually be part of the compact set, which means they're really maxes and mins. Right? And that's cool because it means that just like a finite set will always have a maximum and a minimum, a compact set will always have a maximum and a minimum. And for lots of things, like when we start talking about calculus problems, about knowing when something has a maximum and a minimum, like you saw in Calculus 1, when you literally talk about a relative max or a relative min, or better yet, an absolute max or an absolute min for some function. What's really going on there, that whole story, is really about compact sets.